How do birds navigate? Though I'd like to say that they wing it, the answer is magnetoreception. If a cinnamon roll is in front of you, the smell of cinnamon triggers our odor receptors so that we can respond appropriately. Similarly, the Earth's magnetic field causes a chemical reaction in the bird, triggering a biological signal indicating direction. But the Earth's magnetic field is 40,000 times weaker than a bar magnet. So, to understand how it causes chemical reactions, imagine trying to tip someone over only using a finger. Nothing happens. But if they are already balancing on one foot, the finger, which represents the Earth's weak magnetic field, has an impact. Unfortunately, we don't have an atom doing yoga to put them in an influential state, but we do have the radical pair mechanism. In this atom, each electron is paired up except for one. This atom's a radical. Because electrons have a property called spin, it makes them magnetic. Due to the Pauli exclusion principle, paired electrons must have opposite spin, canceling their magnetism. But the lone electron is still magnetic. For a little bird's eye view, their retinas have a protein called cryptochrome, consisting of free radicals. A radical pair can be created using molecules A and B, which have a HOMO and LUMO. When light enters the eye as photons, it's absorbed. This excites an electron from the HOMO to the LUMO, allowing an electron transfer which breaks the covalent bond, producing an unstable radical pair. It will either recombine to form the molecule that was just broken or form a new one, but which reaction takes place? As the electrons are unpaired, its spin can flip, making them in a triplet state. If they have opposite spin, they're in a singlet state. In a triplet state, the radical pair can't recombine and must form a new molecule. In the singlet state, it can recombine. So the spin state decides how many new molecules form. To decide if the spin state changes, understand that energy is discrete in quantum mechanics and there are two allowed energy levels. Because protons and neutrons also have spin, making them magnetic, there is a magnetic interaction between the nucleus and the lone electron, known as hyperfine interaction. This messes up the overall energy of the whole system, causing the lone electron to be in a superposition of all the allowed energy states. It can either collapse into a singlet or triplet state, and the probability changes with time. As these oscillations are caused by the interaction of two magnetic fields, if another magnetic field is introduced, these oscillations change. But if the magnetic field is pointing in a different direction, understand that hyperfine interactions are anisotropic, meaning that as the direction of the Earth's magnetic field changes, their strength also changes, which in turn affects the oscillations from singlet to triplet state. As the spin states affect how many new molecules form, and this amount changes if the oscillations vary, different amounts of this molecule may indicate different directions. So, the next time someone calls you weak, give them a little direction.